Good morning, Astronomy 1010. Welcome to your third week of lecture. Today and Wednesday, we're going to be learning about the history of astronomy. If you've taken my Astronomy 1020 class, this material was pretty much not included whatsoever. So this should be new to everyone who's taking my course, whether it's the first time or return students who've taken the other half. Um, Today, what we're going to do is we're going to spend some time thinking about early astronomy, especially Greek astronomy. And then I'm hoping that on Wednesday, we'll move into the Copernican revolution and study some not super modern, but slightly more modern astronomers like Copernicus and Galileo and Johannes Kepler. Today, our lab will appropriately be on eclipse prediction. Ancient Greeks were able to predict eclipses and had some success with this. They had a very sophisticated understanding of astronomy, as a matter of fact. And today you will learn that predicting eclipses is not as easy as it might sound. So make sure you print out, as I told the students before class, make sure you print out at bare minimum this page from our eclipse predicting handout. 4-5 is what you will be writing on and turning in. During the lab, I will be using this data table of eclipse data. You don't need to print that out or turn it in. So you can follow along with mine, or you can kind of have it up on your computer as we go. There are some instructions, but I'm going to walk you through them, so you shouldn't really need to read those. Okay, so let's start by thinking about what we've learned about in the past week. We learned about stellar coordinates, how to track the positions of the stars, the sun and the moon, and timekeeping. But we didn't talk too much about planets. So let's see what I did. Oh, you found it, John. Cool. All right, I'll have to check out that tea shop. I wanna get there. Um, so let's see what you guys remember. How many planets are visible to the naked eye? I think we talked about this before.
Wasn't it 5?
Yeah, Ryan, do you remember which ones they were?
Mercury, Saturn, Jupiter, Mars, and Venus? No.
Exactly. And did we talk about why, like, if you look at a planet, how do you know a planet is not a star? Because to your eyes, a planet looks like a star. Did I do this before? I did this with one of my classes. I just can't remember if it was you or Astronomy 1020. Did we talk about this?
I think we did, yeah.
Okay, so what are the ways we know a planet is not a star? There should be 3 things here.
How they can clear their own rotational path of debris.
You're thinking of like a modern astronomical definition of what makes a planet. But I'm just thinking about if you are a dude or a dudette or a person and you stand outside at night and you look up at the sky, how do you know the blinky light that you're looking at is a planet and not a star? Because they kind of look the same a little bit.
I take it back. I don't think we talked about it.
All right. Well, let's start with this one. First of all, planets are brighter. If you look up at the nighttime sky and you see a really, really bright star, the chances are you're not looking at a star, you're actually looking at a planet. And so they pop out against the background stars much stronger and more noticeable. You can't help but see them. They're impressively brighter. A second rule of thumb that astronomers use to determine a planet is the rule goes that stars twinkle, but planets don't. This has to do with the star's angular size. The angular size of a planet is significantly larger than the angular size of a star. For example, the typical angular size of a planet is usually somewhere around 1 minute of arc. The typical angular size of a star is usually around 0.05 arc seconds, which astronomers would call 50 milli-arc seconds. Can't spell. Keep in mind that an arc minute is not an arc second. I wonder how many of you are really good out there. Who can tell me in 1 minute or less, how many times bigger is 1 arc minute? Well, let's start simple. How many times bigger is 1 arc minute than 1 arc second?
60.
Good. So the number of times bigger the angular size of a planet is 60 divided by 0.05, 1,200 times larger in angular size. But you want to know what? None of that really matters to your eye, because the minimum angular resolution of the human eye is about 3 minutes of arc. So you can neither resolve a planet nor a star with your naked eye as anything more than a pinpoint, a mathematical dot. This isn't even fair. This is what a star is like, or a planet. They both look like unresolved dots to your eyes. You can detect the light, but you can't see any features on them. Now, because stars are a much smaller pencil-thin beam, they tend to dance around due to distortions of our atmosphere and sparkle. But planets, being slightly larger in their angular size, their light is much steadier. They don't dance around as much. So the rule that astronomers use is stars twinkle, planets don't. However, if you were an ancient observer, an observer of the sky, neither one of these two things would prove that a planet was not a star. You could just say, well, we're looking at a brighter star, and it doesn't twinkle as much because it's brighter. How then did the ancients know that planets were not stars? By the third thing. Anyone want to guess what it is? I might have told you before, honestly. No? No one could even guess or imagine? Someone guessed it right during our lab last week. John's pencil's orbiting around his head, but I'm not clear what that means. Okay. The answer is that planets wander with respect to the background stars. In fact, the Greek word plenitos means in ancient Greek wanderer. And stars do not wander with respect to each other. They stay fixed. And to understand this, it might be helpful for us to look at a slide. Let's go ahead and do that. Let's call up a slide. Excuse me. I think it might be. Why can't I click on you? Okay. I think somewhere in here, I have a slide. Here we go. So you go out at night, and you're in the summertime, you look up and you see the constellation Sagittarius. And not all of the stars in Sagittarius are bright, but there's a grouping of stars that astronomers refer to as the teapot. And no kidding, it actually looks like a little teapot on the sky. And you see the stars of the teapot, and then you see this really, really bright star-like object that does not twinkle, and that's Mars. And you catch Mars somewhere above the spout of the teapot. The teapot and Mars rise and set, and you really don't think anything of it other than, oh, wow, that star was really bright and really red, and it's sitting above the teapot. But what happens is if you go out and observe it again on the next night, you see Mars has shifted a little bit east with respect to the teapot and is now near the top of the, whatever you call that part of the teapot. Tea is kind of a theme in today's lecture, I can tell. Okay, so you're at the top of the teapot and you think, boy, that's funny. I thought Mars was a little closer to the spout yesterday. Maybe I'm crazy. Then you go out the next night and you say, okay, no way. Mars is definitely moving with respect to the teapot. And a night after that, Mars drifts a little more eastward. Then you start thinking about it and you think, damn, that's kind of messed up. This one star is kind of special compared to all these other stars because all these other stars are dim and they're kind of locked in place. But this planet is able to drift with respect to those stars. It's almost as if it has free will. Maybe it's a god. Maybe I should worship it and it will bring me victory in battle. Who knows? People, the ancient Greeks, literally worshipped these planets as their gods. Their gods were not abstract old men in the sky who got mad at you when you said a swear. These gods were real physical objects that they could see wandering crazy around their sky. What really screwed up the ancient Greeks is that the planets would drift eastward night after night, but at key times of the year, the planets would suddenly change direction. They'd stop moving east, and then for a period of a couple of weeks or so, they'd move westward along the ecliptic night after night. Then they would change their minds and change direction again and go back. And this is what is known as retrograde motion. The desire for Greeks to understand retrograde motion so that they could understand their gods is the driving desire to invent a science of astronomy. Even the development of physics and mathematics comes from the desire to understand this problem, the problem of retrograde motion. And we will define retrograde motion as a temporary westward drift along the ecliptic made by planets. Retrograde motion is kind of a buzzword. It's one of the ways that ancient people knew that planets were different than stars. I'm just going to give you guys a moment to catch up, and then I want to erase that. Here I go, I'm erasing. Today, our lesson concerns itself with the history of astronomy and how it developed. By learning about the history of astronomy, you not only learn why it is that astronomers think the way they do and how our development of the cosmos has changed over time, but you also learn about the history of humanity, because astronomy is probably the oldest science there is. It goes back even further than the concept of science itself. Astronomy is literally thousands of years old, and probably even older than that, as old as humanity itself, because we've constantly looked at stars and used them as our ancient clocks to keep track of time. Now, although we want to talk mostly about Greek astronomy today, it's worth mentioning that there are evidences of astronomical study that go all around our world. And if you poke around, you can see examples of ancient observatories. For instance, y'all might have heard of Stonehenge before. In England, there's a circle of massive stones that must have taken quite an engineering feat to erect. And they're arranged in this circular form. When the Romans invaded England, they found this stone circle and a bunch of druids conducting some pretty evil human sacrifices and other such things on them and thought, boy, these savages are really insane. They're worshiping trees. They're stabbing people on these stone altars. And egads, how the hell did they erect these stones anyways? This looked like a pretty sophisticated operation. The Romans didn't know much about it. Now, over time, people forgot who actually built these giant stones or what their function was. They thought it was mostly religious or mythological. But at some point, a famous archaeologist who knew about astronomy realized that he could account for the positions that the stars had drifted by due to precession. You'll remember I talked to you guys about precession as the slow drift of Earth in a circular motion for 26,000 years, and it changes the configurations of the stars. If you wind back the precessional motions of stars to when Stonehenge was being used, they found all of these really cool astronomical alignments. For instance, at the so-called heel stone, the heel stone would align itself with the rising of the sun on the summer solstice, telling us that they knew what day the summer solstice was, and they realized its astronomical significance. And these other Aubrey holes that were around the circle seem to align with other key alignments, like the rising and setting of the moon, the sun at the winter solstice, and the sunrise at the summer solstice, and other configurations. In other words, this Stonehenge, what it really was a giant astronomical clock, an observatory to keep track of the motions of the stars. This tells us that ancient people were aware. Think about it. You guys had enough difficulties. John was saying before class, I'm not going to lie, Brennan, this stuff can be kind of confusing your first time around. Hell yes, it is. It's difficult to figure out how the sun moves through your local sky. These people, these druids, already knew it, John. They had already taken they didn't really take the class, they just lived it, right? We see other examples of astronomy happening around the world. Let's take the ancient Aztec city of Tenochtitlan, where their central temple, called Templo Mayor, was constructed such that their two towers bracketed the sunrise on the day of the spring equinox. So if you lived in this society here in this city, on the day that the sun rose on the spring equinox, kind of Indiana Jones-like, it would shine a beam of sunlight right through the two temples and illuminate the central courtyard. The message of that beam of sunlight would have been clear to any of the people living in that society. The message was, get up off your ass, get out in the field and start planting some corn, or we're all going to starve come harvest time. So this entire temple was constructed around the rising of the sun at the spring equinox. And I could go on forever. There's the Anasazi people in New Mexico have this thing called the sun dagger. If you're a serious rock climber, you climb some butte, and at noon on the summer solstice, a dagger of sunlight pierces the center of this target. That's obviously not random. That tells us that the Native Americans who occupied the Southwest were clearly aware of the date of the summer solstice and had devices to mark it. We see Mayan temples dedicated to the phases of Venus. The Chinese astronomers, the ancient Chinese astronomers, took very, very careful, detailed maps of the stars in the sky. This is the observatory, the Royal Observatory in Beijing, where thousands of years ago, Chinese astronomers mapped out all the stars in the sky. They even famously mapped out a new star, a supernova, in the year 1054 AD. To them, it looked just like a new star appeared in the sky, but they marked its careful position, probably in terms of right ascension and declination, and they said, hey, this is a new star, that's pretty wacky. And thousands of years later, when we developed radio telescopes, we pointed to the same position, and we discovered this huge shredded cloud of plasma that told us that some star had exploded there. And because the Chinese astronomers kept records of the date of the new star's appearance, we were able to time the expansion of the supernova. So it's kind of like a collaboration through time between us and the ancient Chinese astronomers. Very cool stuff. So astronomy is as old as humans itself, especially agricultural societies who required the sky as a sort of giant clock to keep track of their planting cycles. Despite the fact that all of these different societies kept careful records, or maybe not careful records, but kept track of the motions of the sky, today we're going to focus our lesson on the history of astronomy with Greek astronomy, because the ancient Greeks they had a way of looking at the world that was different than their contemporaries. It was a much more secular way of looking at science. Or I say science, but science as a concept wasn't really invented yet. They had a way of looking at nature which was more secular. And as an example of this, it is considered that the first person who constructed some type of quasi-scientific statement, the first truly scientific question was posed by the ancient Greek philosopher Thales of Miletus. And he asked the question, what is the basis of nature and its variety? By which he meant, where do we get all the different things on Earth? Where do we get the rocks and the trees and the squirrels and the spiders? And he decided that the answer was everything on Earth and everything in the cosmos is made out of water, which is a pretty funny thing to say. On the other hand, I guess it turns out that human beings are made of mostly water. And also, he was an Ionian philosopher. He lived on a little island surrounded by water, so maybe it was natural for him to believe that the entire universe was made of water. The reason why this is considered by historians to be the first scientific question ever posed was because the answer was the first recorded instance of someone trying to explain a thing in nature. I guess the thing was everything in nature, in terms of another natural substance like water. So for instance, before Thales, if you tried to explain lightning, other civilizations might have said, well, why did the thunderbolt strike my hut and catch it on fire? And the answer they came up with might have been, Zeus Poseidon was angry at me because I ate too many chickens at the relay race. So he decided to smote my hut with a thunderbolt, right? That is a personification of nature, which imagines sort of these mythological, superstitious reasons for things to happen. But as silly as it is, to try to explain something in nature being based on another physical substance like water, water is a thing that anyone can go out and observe or test or explore with. It doesn't rely on any non-observable, mystical origins for its for its explanation of things. So this is considered to be today one of the hallmarks of science. Science tries to explain natural phenomena, things in your universe that you can touch and taste and observe with your eyeball and your telescope. You try to explain those things in terms of other natural phenomena so that other people can also investigate it, and it doesn't rely on your divine intuition about the gods or something like that. Excuse me. So, in fact, after Thales proposed that everything was made out of water, another astronomer came along, and his name was, sorry, I said astronomer, but it's a philosopher would be more appropriate. And Anaximander famously came up with a concept that the celestial sphere and the Earth were floating in empty space. And Anaximander suggested that, unlike Thales, who said everything was made of water, he suggested that everything was made out of fire. And then a third philosopher came along and said, no, everything's made out of earth material. And a fourth one said everything's made out of wind. And then Aristotle came along and he cobbled together the four arguments and said, maybe each of these people have an argument to be made. Maybe some things are made of earth, some things are made of wind, some things are made of water, and some things are made of fire. And thus the four primeval elements were born, which in a weird way was kind of like humanity's first periodic table of the elements, right? So people were already arguing with each other and fighting over which natural substance was the best description of nature. And that sounds to me very much like what modern science is. People politely arguing over which natural explanation of things is the correct one. Also keep in mind, if the Greeks had developed the idea of Earth as a sphere in empty space, and had developed the idea of a celestial sphere with stars rotating around it, that means they were different than other civilizations who believed in a sort of mythological worldview where the Earth was flat. And of course, all of these ancient cosmologies are funny because in the ancient world, if you believed in a flat Earth, like some people unfortunately still do today, there's usually considered a very definite direction of goodness, right? Where anything up towards the heavens is considered good, and anything down towards the earth is bad, right? So, of course, the Greeks had no use for anything like that. They kind of had this idea. They kind of invented the concept that Earth was the sort of center of the universe, floating in empty space, and it was surrounded by a sphere of stars and some planets that were all rotating, which is pretty wild to think about it. Okay, today we are going to focus on Greek astronomy, and let's talk about that and take some notes. One of the important ideas that was developed in Greek astronomy was an idea we refer to as geocentrism. Geocentrism is a, I don't know, hypothesis or a theory in which you have an Earth-centered cosmos. I don't want to say solar system because for them, the solar system and the universe were the same thing. So I say cosmos to imply this was as big a concept as they had for what the universe was made out of. And what's interesting is that the Greeks actually had correctly developed the order of the planets. They had Earth as the center, followed by the orbit of the moon. Let me just kind of show you a picture here, or rather a diagram of the Greek conception of the solar system. Notice not what's wrong about this, but what they got right. Earth is at the center, followed by the orbit of the moon, then the orbit of Mercury, Venus, then comes the sun, Mars, Jupiter, Saturn, and then the stars were stuck to a crystalline sphere which rotated at the very edge of the cosmos. So an Earth, Moon, Mercury, Venus, then came the sun, then Mars, Jupiter, Saturn, and then what we would call the sphere of fixed stars. So what do you guys notice? I'm hoping this is an obvious question. What do you guys notice about the order in which this solar system is laid out? Any thoughts here?
If they swapped Earth and the moon with the sun, we'd be in order.
More than just that, bud.
Oh, wait a minute.
Sorry, I'm trying to fix my handwriting here. Okay, yes, Earth, Moon, Sun are in the proper order, but if you keep thinking about it, they got more than just that.
No, I mean, if you put the sun where the Earth and moon is and put the Earth and moon where the sun is in that list, they'd all be in order.
Right. Also, if you think about it, that means they got the ordering of the planets correct, right?
Right.
But John, why don't you slow down and think about what that means for a second? How the crap did they do that? After all, there's no field. When you look up at the stars, you just see here's a bright planet wandering around, and here's a bright planet, and here are some stars. How the hell did they know that one planet was closer or farther than the other? Can you think of any observational way to do that? Can you be as smart as an ancient Greek philosopher?
No.
Exactly, because these guys were really effing smart, and they had a very sophisticated understanding of things. Actually, there is something you learned about in last week's lecture that would tip you off. You'll never guess what it is. Let me show you a picture here. It has to do with the synodic periods of the planets. What the hell is a synodic period again? I can't remember. Someone remind me what a synodic period is, because I'm sure you all forgot. You might want to look in your notes. Let's do some work. Let's try.
It's the time between planetary oppositions.
Okay, sounds good when you talk like that, but what does that mean?
It's the time for the planet to circle the celestial sphere relative to Earth.
Yeah. It's sort of like how long it takes the planet to come back around to the same point in your sky. Now let's think about this. If you have a planet like Mars, you might line up with it every year and a half or so. But as a planet gets farther and farther away from you, its synodic period comes closer and closer to 1 year. As an example, let's try to imagine Pluto for a second, right? Pluto, of course, wasn't one of the ancient world planets, but Pluto is a really great example because its period is like 252 years. So let's say I do Sun, and then Earth, and up here is Pluto. And right now, Pluto is in opposition, where it's opposite the Sun. Let's imagine what happens in 1 year. In 1 year, Earth goes around the Sun, but because Pluto's period is 252 years, Pluto is only going to go 1/252th around its orbit, which is like barely even this much. Like it hardly even seems to move relative to Earth. So when Earth comes around in a year again, Pluto will be back to its same position in the sky. In other words, the synodic period of Pluto is probably like 1.005 years. I don't know what it is, but it's probably something stupid like that. It's wicked close to 1 year. In other words, the farther away you get from Earth, the slower you seem to move around the sky. Actually, not slower, the quicker you seem to move around the sky because your motion is just a reflection of the motion of Earth, right? I wonder if anyone followed me on that. I don't feel like you guys did, but I tried, okay? Look, the Greek philosophers were intelligent observers of the sky. They knew that the closer a synodic period got to 1 year, the farther away they should be, and therefore that's how they figured out the orderings of the planets. It was based on observation. That's very sciencey of them. Now, we're going to study a couple of key philosophers who had tremendous influence on the Greek geocentric model of the solar system. I'm not going to expect you to remember everyone like Anaximander or Thales of Miletus, but I will expect you to know the people that I'm about to write down the board, as they are very important. I'm going to erase this here. So, people that we're going to study in detail: Eratosthenes was a clever geometrician and geographer and astronomer who was famous for having measured the circumference of Earth. And this is a nice thing because it's a cute example of how you can use your astronomy knowledge to do something really practical and figure out how big the planet you're living on is without having to travel all the way around it. It's also going to be the basis of a homework problem and probably one exam problem. We also are going to study Plato, perhaps the most famous of the Greek philosophers. We will study Aristotle, and we will study an Arabic Greek astronomer, mathematician known Ptolemy. And these are the people and their discoveries and their contributions to astronomy are what we'd like to cover today. So this is where I'm going. And these are the people I expect you to know some stuff about. Once I get into Plato, I'm going to want to talk about Aristotle, and I'm going to want to talk about Ptolemy. These guys are all connected to each other. So let's take a moment here just to discuss Eratosthenes and a method by which you might measure the circumference of Earth, okay? Eratosthenes had grown up in a city south of, do you guys know about the city of Alexandria? The city of Alexandria in modern day Egypt was a site of ancient learning. And it was kind of like a Boston, Massachusetts of the ancient world. In addition to having many philosophers and scholars who studied there, they had something known as the Great Library at Alexandria, which during its apex was said to contain up to 500,000 papyrus scrolls featuring all of the wisdom of the ancient world. The plays of Aristophanes would be stored here, works by Pythagoras, works by Aristotle and Plato. Famously, it burned down around 412 Common Era when a mob of religious zealots attacked it for whatever reason and set it on fire. And much of the wisdom of the ancient world was lost in this great fire. So it's kind of a scary thing to think about, is that we can learn things, and then if we forget them, we can go backwards again. It has happened several times. Some of the work survived, and the people that we know about, we know the best because some of their writing survives, like Plato and Aristotle. But they make references to other philosophers at the time who had discovered things, and they're tantalizing hints of some of the knowledge that might have been lost. One that did survive was the story of Eratosthenes, which is what I was trying to get into just now. So let's talk about what he did. Let me kind of jump. I'm doing this a little bit out of sequence here today. He was around 200 before Common Era. And famously, he had grown up in a city called Syene, which was located south of the city of Alexandria. And he remembered that when he was a boy, on the day of the summer solstice, when the sun was as high in the sky as it could get, that he was able to see the water at the bottom of the town well. Later on, when he was an older man, he lived in the city of Alexandria where he studied, and he remembered observing that on the day of the summer solstice, he could not see the water at the bottom of a well. And this made an impression on him. He realized that it had to do probably because of the curvature of Earth. Now, there were philosophers before him who had suggested Earth was round. Namely, Aristotle had argued it, but probably one of the first people that argued it was the ancient Greek astronomer Pythagoras. He's famous, of course, for his Pythagorean theorem, a squared plus b squared equals c squared. But he also did many other things besides that. For instance, it's recorded that he had taught his students that Earth was spherical in shape. One of the ways that Aristotle argued that Earth must be a sphere is kind of a clever one. Where's my damned internet here? He noted that during a partial solar eclipse, the shadow that Earth made on the moon was spherical in nature. I'm sorry, not a partial solar eclipse, a partial lunar eclipse. Apologies. That's the shadow of the moon. A partial lunar eclipse. Geez, that's not very smart of me. Here's a picture of a partial solar eclipse. And one of the things Aristotle writes is, look, you can see the shadow of Earth passing across the moon, and you can see that it's curved. That in itself is proof that Earth must be a sphere. Another reason why, and I can't remember if you had the class where someone asked me about the Flat Earth Society. It might have been my other class. If you live on a flat plane and you walk north and south, the angles of the stars wouldn't really change that much. But on a spherical Earth, your latitude really affects the positions of the stars. For instance, you learned in your last class, or one of your last classes, the altitude of Polaris is equal to your latitude. That's only possible if you live on a curved surface. So there are many good arguments for why we should be living on a sphere, but at the time, no one had any idea about how to go about measuring it. Here's what Eratosthenes did. Let's go through his argument. Let's start by drawing a little circle. And what we're going to do is we're going to put a dot in the center of our circle, and we're going to make two sticks, one which goes to Syene in the south, and the other which goes to Alexandria in the north. So draw sort of radius up here that will be sticking, and we'll put a stick in the ground. This will be the city of Alexandria, which I will label with an A. Let me get a little bit closer here. Okay. And here, I'll draw the radius of Earth going out to another city. This is Syene. Okay. And what he did is he recreated the experiment by placing two staffs or two sticks into the ground. And he wanted to measure the shadow that the sticks would make on the ground, because that would be easier than trying to mess around with a well. Now, in the ancient city of Syene, he could see the bottom of the well. And so on the day of the summer solstice, the sun actually reaches the zenith and the stick casts no shadow. Let's draw a ray of light headed towards the sun. So in the same direction as the stick, the sun appears at the observer's zenith. Now here's where the special astronomy knowledge comes in. Eratosthenes knows that all rays of sunlight that reach the Earth are essentially parallel to one another, because he knows that the sun is so far away that only rays that are traveling on a parallel track will be able to strike Earth. This is a key concept in astronomy. So he knows that if the sun is directly overhead in Syene, the rays of sunlight which are striking the stick in Alexandria need to be absolutely parallel to that one. Now, I could have drawn any ray I wanted, but I chose to draw a ray that hits the bottom of the stick. This also points towards the sun. The goal that he had was to measure the angle between the stick and the sunlight. I'm going to call that angle theta. So here, theta is angle between the sun and the zenith. Now, he knows there's this theorem in geometry. If you have two parallel lines, like in a train track, and you slice through them with a perfectly straight stick, you know that this angle and this angle and this angle and this angle all have to be equal to each other. I think they call this theorem alternate interior angles in geometry, but it's been a while since I took my geometry class. But if you cut parallel lines with a stick, the angles that they make with the parallel lines have to all be equal. He set about to measure this angle, but what he was really interested in was this angle. This angle, the angle from the center of Earth to the two cities, happens to be the same as that angle by alternate interior angles. So I don't know if you guys can see that, but if I make this ray to the sun, this angle and this angle are the same. This angle and another angle down here are the same. So he knows that the angle between the stick and the sun is the same thing as the angle between the two cities. Why would that be interesting to him? Check out this argument. Suppose you know the distance between Alexandria and Syene. I'm going to call that capital D. In fact, because he knew he was going to need the distance, he paid a friend of his a bag of shekels or something to walk the distance from Syene to Alexandria so that this distance could be measured and well known. And then he made the corresponding ratio argument. He said, let's imagine this little slice here is kind of like a piece of pizza. That angle theta will be some percentage of 360. But the distance d between the two cities will be the same percentage of the circumference. And I don't know if that makes sense to you guys, but if you imagine it like a slice of pizza, if this angle is 1/8 of 360 degrees, this distance will be the crust here of your pizza will be 1/8 of the total circumference. But he knows the distance because his friend marched it out, and he knows theta because he measured it with the stick. And now he can do some algebra and he can rearrange to solve for an equation that I call the method of Eratosthenes. I flip the circumference up, the angle down, and the 360 across to get this formula. The circumference is 360 degrees divided by the angle times the distance. And this is cool because the circumference is not that easy to measure by walking, obviously, but the angle and the distance are doable. Now, famously, when he did it, he measured an angle that he recorded as 70 degrees. But here's where the problem, sorry, not 70 degrees, 7 degrees. Jesus, what's wrong with me? 7 degrees. But the units that he used to measure the distance between the cities were not kilometers. They were another unit that was used in ancient Greece. They were called the stadia. So I believe when Eratosthenes did it, sorry, I forgot what that slide was. I'm not sharp today. 46. So famously, when Eratosthenes did this problem, his friend measured the distance between the two cities as 5,000 stadia. We don't exactly know what a stadia is because, like many of those books in the library at Alexandria, the unit of Greek stadia were lost to time. Modern historians have just guessed that perhaps a stadia was the length of a typical Greek stadium, which are not uniform by any way. So they went out and they measured the lengths of all these different Greek stadia and took the average. And if you do that, you get one stadia is about 0.2 kilometers. And if you plug in that value, Eratosthenes figured out that the circumference of Earth was 40,000 kilometers, which is really, really close to our modern value of 42,000 kilometers. So he only had like a 2% error, despite the fact that he was only using sticks and a guy marching the distance between the two. It's kind of impressive, actually. The idea is that this thing worked, you know, and it's a cool demonstration of how a little bit of knowledge about the angle of the sunlight and knowing that the Earth is a sphere can let you perform a simple experiment which can help you calculate the size of your planet. That's pretty wild if you think about it. Anyways, I wanted to get that formula into your notes. In our class on Wednesday, we'll do a problem on the method of Eratosthenes. It's not too important to try a sample problem now because this formula is just so easy. Can I erase? All right. Okay, so I got that out of the way. That was kind of its own little module. Now let's talk a little bit about sort of the model of the solar system that the Greeks came up with and the development of geocentrism. The next philosopher that we're going to talk about is considered by some to be maybe one of the greatest philosophers of all time, Plato. And I've got a copy of his book somewhere on my shelf. Let's see if I can find it here. I usually have it handy for when I want to talk about this. My books have gotten jostled around by all my friends recently. But somewhere in here, I have a copy of Plato's Republic. And, you know, it's if you're going to be a college student, at some point you probably have to take a philosophy class or an English literature class, and they are going to make you read Plato's Republic. It's kind of a classic. And Plato's Republic is actually, despite being a book that was written thousands of years ago, is a really fun book to read. It's not boring at all. It starts off with Plato chronicling the adventures of his teacher, Socrates. And it starts off with Socrates leaving some Athenian Olympic Games and a bunch of young men crowding around him to sort of have an intellectual discussion. In ancient Greece, a cool thing to do would be to hang out with your friends or some wise teacher and sort of have an intelligent discussion about things. In fact, these kind of became the models of our modern day universities. Plato famously developed the first lyceum or school where a bunch of young men would get together and have intellectual discussions. And these became weirdly the basis of our modern universities. They even carved on the walls of Plato's first lyceum, "Let no one unversed in geometry enter these halls." If you didn't know geometry, you were considered an uncool person who is not to be hung out with, okay? Now, in Plato's Republic, Socrates is leaving the Olympic Games, and the young men crowd around him and they say, "Hey, Socrates, how'd you enjoy the games?" And he said, "Oh, yeah, it was a lot of fun. I watched the relay race." And they said, "Well, what are you doing now?" And he says, "Well, I'm going home because I'm old and I want to go to bed." And they said, "No, no, no. We were hoping to engage you in an intellectual discussion." And Socrates says, "Well, I don't have time for that. I feel like going home." And the young men crowd around him and say, "Well, is it not true that there are more of us than there are of you?" And he says, "I have to admit, this is a correct observation." And so the young men say, "Well, then, if necessary, we could compel you by force to have an intellectual discussion." And he says, "Well, I have to admit that is also true." And they say, "Well, then there's no getting out of it. You have to have a discussion with us." And thus begins Plato's Republic under the threat of violence. It's really just a fun and easy book. You would think that because it was written thousands of years ago, it'll have some arcane language or be hard for you to understand. I swear to God, it's as easy to read as a Stephen King paperback novel. You could read the damn thing on the beach. And what impressed me when I had to read it as a student was how relevant it seemed to my modern life and how many things he talked about were things that I was just naturally interested in. And they cover all kinds of interesting subjects like what is truth and what is justice. And he even eventually touches on astronomy a little bit. And that's what I want to talk to you about today is how Plato's thinking about astronomy influenced us for thousands of years to have somewhat incorrect views of planetary orbits, actually. Okay, so in Plato's book, The Republic, Plato develops this concept called the form. And the form was kind of like the most idealized, abstract qualities that a thing could have. For instance, there could be a form of a bird, the most sort of unifying generic composition, feathers, beak, wings, whatever. One example that was given to me that was important to Plato was the form of a circle, right? So if I wanted to, I could make a circle with this frisbee here. And because I traced it, it's a reasonably good circle. But this circle is not a perfect circle. It doesn't quite connect on this end. It might be a little lumpy at parts. The closer you inspected this circle, the more imperfections you would see. Most of the time when people draw a circle, when they do it freehand, they do it like this. And this circle clearly has even more imperfections than that one. Even if you draw a circle with a computer program or with a compass, it is still pixelated at the tiniest levels. So Plato argues if you look at all the circles that people draw, none of them are perfect circles. They're all flawed in some ways. But the thing that we were all considering when I drew this circle is not the actual lumpy bad circle that you see here, but everyone kind of intuitively knows that I'm referring to a perfect circle, an abstract idealized circle. This is what Plato would call the form of the circle. Now, Plato's idea, which is kind of mind-blowing, is you might think that all the real circles are imperfect, but the real circle is not any of these. It's not the circles that people draw, the circles you see. The real circle is the circle that's in your mind. The abstract idealized circle is the only thing that actually exists. Okay, that's why Plato is freaking cool. But unfortunately, it led Plato to the idea that there were forms of things that were perfect and not like the kind of nasty real circles that we see on planet Earth. So let's take a couple of bullet points about this. Like many Greeks, Plato was obsessed with circles, and he believed that circles were sort of like perfect geometrical forms. And if there was anywhere, Plato argued, where you would find a real perfect circle, the form of a circle, it would be in the heavens. The heavens, he argued, were, here's a fancy word, immutable. The heavens were immutable because they were timeless and unchanging. And of course, that's not actually true, but Plato thought it was true for sort of simplistic reasons. One of the ideas is, if you look at the orbits of the planets, remember that as far as Plato was concerned, the planets and the stars would return to their same positions with clockwork regularity. If you waited a year, Sagittarius would come back up again, and Mars would go through its retrograde loop again, and all of the heavens were on this kind of perfect clockwork machinery, which as far back as anyone could remember, they could still see the same constellations rising and setting. This led him to argue that the heavens were perfect, and therefore the orbits of planets had to be perfect circles, otherwise the cosmos would come unwound. In other words, he developed this kind of nasty idea, which still persists in some major religions today, that the heavens are a perfect abstract world where the earth is a nasty, dirty, corruptible world that is not perfect. That idea is actually pre-Christian and goes all the way back to Plato and the ancient Greeks. So Plato believed that the orbits of planets were perfect circles, that the heavens were not the same as Earth. He even believed the planets themselves were perfect spheres. Now, that's pretty wild if you think about it, because, you know, like a modern day Christian conception of God, if you just type it into Google, would be something like you see in the Sistine Chapel, right? You'd imagine some old man in the sky with a beard sort of poking you in the finger and making sure you don't say bad words or whatever it is that God's supposed to do. But if you were the Greeks, God wasn't some old man in the sky with a beard. First of all, there wasn't God, there were gods. And their gods probably looked more like this. They probably looked more like the obelisk in 2001: A Space Odyssey, just some kind of creepy, faceless, geometrical sphere floating in empty space. That's a lot more creepy if you think about it than other people's conceptions of things. I mean, they literally believed, like Plato, that their gods were just these giant, faceless spheres. And the spheres had to be blemish-free, completely free of any imperfection whatsoever. They were perfect spheres, free of imperfection. And because Plato was so clever, and because his arguments seemed to make sense, this idea about the orbits of planets influenced not just several generations of Greeks, but it persisted all the way up into the Middle Ages, these ideas about the orbits of planets. Now, of course, there's just one problem with this theory. And what do you think that problem is about these perfect circular orbits? And I'm trying to give you a hint right here in slide 104. What would be one sort of observational piece of evidence that might challenge Plato's idea about perfect circular motion?
The irregular, perfect circular motion that's going on there.
Explain. I think you are saying what I want you to say, John, but say a little more of it. What type of motion are you talking about? Use a fancy vocab term for me.
I'm not smart enough for fancy vocab terms.
Well, you don't have
He
to.
probably has one of these. There you go. Jenna's smarter than me.
Jenna?
Oh no, I was just gonna say the retrograde.
Yeah.
Motion?
So what's up with this retrograde motion stuff? That don't look like no perfectly circular motion, does it, Jenna? No.
No, it's like
Now-
skewed.
What do you think Plato would have said if you, Jenna, could go back in time like Bill and Ted's Excellent Adventure? I think they actually meet Socrates, but Plato would have been around then, right? Socrates, that's what they say. Anyways, what do you think Plato would have said to you, Jenna, if you were a pesky student and you pointed out, hey, Plato, your perfectly circular orbits are cool and all, but what about retrograde motion? You know what Plato would have said to you? He would have said, shut up. You're confused because you're trying to observe things and you shouldn't trust your senses. That's not the right way to investigate nature. This is a way in which Greeks were in some ways very unscientific. Modern science seeks to test hypotheses by comparing them to observation. Plato believed that your senses were, he said, a motley mob that was likely to confuse you. Jenna, if you're looking up at the sky, you're going to get confused. That's not the right way to investigate nature. You've got to use your brain and just think deeper about the problem. Okay, Plato, whatever. But people were still worried about the retrograde motion thing. What the hell are we going to do? Plato is clearly smart, and he realizes that the heavens are these heavenly perfect worlds that have to go around in perfect circles. And yet, we can't help but notice that the planets do not seem to be doing that. Let me show you what the Greek solution to this problem was. Allow me to introduce an invention that wasn't quite made by Aristotle, but was made by some friends of Aristotle, and he actually worked on the problem a bit. So I'm going to lie to you and tell you that Aristotle invented it, because it's easier than telling you the truth. Let me introduce the epicycle, okay? What they did was they put the planets onto secondary circles which rotated backwards in relationship to the main orbit. And by rotating the planet backward, they could make the planets go through retrograde motion while still achieving Plato's idealization of only perfect circles making up the heavenly motions of the planets. So they really contorted themselves here with an epicycle to sort of make sure that Plato could have his perfect circles while describing retrograde motion. And this epicycle became one of the hallmarks of Greek astronomy. So let's talk about the next astronomer in a row, and I'll define those epicycles. Plato was the student of Socrates, and Aristotle was the student of Plato. So Aristotle learned his philosophy from his master Plato. I'm going to erase this here, okay? Now, sometimes people will debate over who is the greater philosopher of the ancient world. Was it Plato or was it Aristotle? I'll tell you where I come down on that debate. Plato is definitely a lot more fun to read than Aristotle because, as I mentioned, if you read the Republic or one of his other works, they're not complicated. They're very lucid and straightforward, and they're clever. I can remember in that same course where I learned about Plato, trying to read Aristotle. I still have that in my shelf, but I'm not going to hunt for it because they're all mixed up right now. I can remember spending maybe 2 to 3 hours just trying to read a single paragraph of Aristotle because it was so long and dense and compact with this sentence structure that was hard to get through, that you literally, to read a passage in Aristotle could take you hours just to kind of figure out what he was to understand what he was saying. If you are willing to push through it, however, there was deep and cool wisdom there. And there's a reason why people think that Aristotle might have been the greater philosopher, because he just wrote so much more and he analyzed problems and he kind of picked up where Plato left off. He was actually a little bit more scientific in a way than Plato was. As an example of something cool that Aristotle did for us, Aristotle invented the syllogism. I don't know if you guys have heard of this before, the Aristotelian syllogism, but you probably have. It goes like this. If A implies B, and if B implies C, then ... A implies C. That's pretty wild if you're the first person to think this up, because this symbolic logic is the basis for computer science and mathematics and all kinds of other things as well. That's just an example of one of the things that Aristotle did. He also studied the orbits and motions of the planets. And what was cool about Aristotle is he attempted, oops. Wow, I can't spell today. Actually, he didn't attempt to do it. He actually did. He constructed a working model of the Greek geocentric cosmos. And this is something that made Aristotle way ahead of his time in terms of his contemporaries. Today, people often think of science, physics, astronomy, chemistry as being an attempt to create a working model of nature. In other words, Aristotle wasn't content with Plato saying, oh, the retrograde motion is just, you're just confused. Don't look at that too carefully. He wanted to make a model that would use circular orbits, but also be able to predict the positions of the planets. So first of all, Aristotle strongly argues in favor of a few things that Plato believed in. He argued strongly in favor of an Earth-centered cosmos. And one of the reasons he had to do this is, believe it or not, hundreds of years before Copernicus ever put the sun at the center of the solar system, there were other Greek astronomers like Aristarchus who actually argued that perhaps the sun was the center of the solar system. So you might think that heliocentrism was invented by Nicholas Copernicus, but it actually goes back thousands of years earlier. It's just that nobody really accepted the idea. Aristotle argues that Earth needs to be the center of the cosmos, the primary center, and that in addition, like Plato said, the orbits of planets are perfect circles. This is something he learned from Plato, and that, like Plato said as well, the planets are perfect spheres. And I'm going to go over some of his arguments in a moment because they were pretty sophisticated. But for now, something I want to tell you about is the epicycle. So with his friend, he developed the use of these things called epicycles. And once again, this is going to make it sound like I'm saying he invented the epicycle. He didn't actually do that, but he used them, and I'm not going to get into the details too much more than that. Epicycles were a secondary circular orbit on which planets rotate a secondary circular orbit on which planets rotate used to describe retrograde motion. Now, I have to admit, I forgot the exact number of epicycles that Aristotle ended up needing for his model of the solar system, but I think it was something like he used like 50 or more epicycles for his solar system model. So I'll just put that on the side as a kind of side note there. Class, I'd like to ask you, how many rotating objects, can you count them with me? How many rotating objects would the Greeks had to have taken care of?
Nine?
5 planets, 1 sun, 1 moon, sphere of background stars. So you're pretty close. I'm getting 8. Am I forgetting anything? 5 planets, sun, moon, stars. So 8.
That's close.
But he had maybe 50 rotating spheres just to try to be able to predict the positions of them. So what would happen is, if he couldn't actually predict the positions of the planets with one epicycle, you'd add another one and another one and get them rotating at all these different rates until you could actually sort of make the thing work. In any case, Aristotle actually had some pretty sophisticated arguments for why Earth should be the center of the solar system. And I'd like to go over one of them before we move on from there. Did everyone have time to copy that? Okay, so let's do a quick module on one of Aristotle's arguments, because it turns out that the later developments of astronomy ended up hinging upon this. So here is Aristotle's argument for a fixed Earth at the center of the cosmos. And it hinges around this concept that we might call parallax. Parallax is an angular shift in the positions of stars due to a moving Earth. Okay, so let's construct a geocentric model for a moment. I'm sorry. Whoa, let me fix that. Let's construct a heliocentric model for a moment. And this is integral to how Aristotle argued that Earth had to be the center of the solar system. Aristotle writes, let's pretend for just a moment that Aristarchus was right and the sun was the center of the solar system and that Earth somehow orbited around the sun. Consider, he said, the orbit of the Earth relative to the background sphere of stars. And let's take two stars, for example. Let's make them some red stars. And let's put them here, somewhere on the sphere. We'll call the stars A and B, just for argument's sake. When Earth is close to those stars, Aristotle argued, they would have some angular separation between them, like so. And let's call that angle alpha. Now, when Earth goes to the other side of the sun, they're going to make a very different angle. I'll do that one in purple. 6 months later, Earth will be farther from the two stars. And now the angle look like this. Let's call that angle beta. What can you guys see is a difference between alpha and beta? Are alpha and beta the same angle? Is alpha and beta the same angle? Who's got some intuitive skills at geometry? You're supposed to know this because we studied the small angle formula. What happens to the angular separation between objects as you get further away? Someone's got to participate with me here. Otherwise, I'm going to give you
The arc minute gets smaller?
Say that again, John?
The arc minute gets smaller?
The angle, you could measure it in arc minutes if you wanted, but I would say the angle, John. All right, so which angle is smaller, alpha or beta?
Beta?
Right. Because you're farther away, beta would be smaller. Now, let's imagine that you were looking, for instance, at the stars in Orion's belt. That would mean when you were close to the stars in Orion's belt, they would be like that, right? They would be that far apart. But 6 months later, when you got far away from Orion, they would be like that far apart. Their angular separation would be changing on the sky, right? But Aristotle argued that doesn't happen. The angular positions of the stars do not change over the course of a year. Therefore, Earth cannot be moving. That is a very powerful argument. And the argument goes like this. Let's write that down. No shift in the positions of stars basically equals no moving Earth. Students, is the sun really the center of our solar system, or is Earth the center of our solar system?
The
The
sun
moon is.
Yeah, most
Earth.
of us believe the sun is the center of the solar system. So this sounds really good to me. What's the flaw with this argument? This argument is a very potent argument. It makes good geometrical sense. And it's based on observation, so it's very scientific. Ultimately, it's incorrect. But can you tell me why it's incorrect? How can Earth move and the stars not shift their angular positions?
because the whole galaxy is moving together.
It's not about the galaxy, not so much about the galaxy.
Because of how small Earth is to the galaxy or those stars?
That's better. The stars are way more far away than Aristotle ever could have imagined. That's the real issue. So, for instance, remember that the Greek cosmos had the stars just outside the orbit of Saturn. It would have been really weird for them to imagine a cosmos where there was the orbits of all these other planets, and then there was this huge, impossible gap between them and the stars. That wouldn't have made any sense at all to have all that empty space. They just couldn't comprehend how far away the stars were. In fact, believe it or not, stars do this. They do undergo parallax. But the parallax shifts of stars are so microscopic in terms of angle that they weren't first discovered until like 1856 by using a very powerful telescope. So they never stood a bloody chance at seeing any of the stars shift due to the motion of Earth. Aristotle's argument was good and profound, provided you believed in their model of the solar system in which stars were just outside the orbit of Saturn. Unfortunately, because this was a good argument, it led to lots of confusion for thousands of years about whether or not the sun could actually be the center of the solar system. People believed that if they couldn't detect this parallax, then they would have a hard time arguing that Earth moved. Let's see how we're doing on time here. Okay, we'll have time for one more Greek astronomer. There was a gap between Aristotle and the next astronomer. And during this time, people attempted to do different things to improve upon Aristotle's model. But the person who really made it work was this famous Arabic Greek astronomer named Ptolemy. Not the Cleopatra Ptolemy, a different Ptolemy. This Ptolemy was a Greek Arabic mathematician, and he was famous for having developed a complex geometrical model that perfected Aristotle's geocentric solar system. And he wrote a book in which he described this model known as the Almagest. That means the star in Arabic. And this was the textbooks used by astronomers for the next 1,500 years. Let's take a few notes about this here. Okay. So our last geocentric philosopher was Ptolemy. Arabic Greek astronomer and mathematician. He was famous for having developed, or you might say improved, a working model of Aristotle's geocentric solar system. In fact, some people will refer to it today as the Ptolemaic Aristotelian model of the solar system. You can think of it as the ancient Greek model of our solar system. He famously required even more epicycles to pull it off. He used a set of over 100 rotating spheres to pull this off. But what was crazy about this model is that it actually worked. And what do I mean by it worked? It means that he could predict the motions of planets and stars. He also could predict eclipses and other such things. He famously put it into a book The book was called The Almagest. You can actually still buy this book and read it today. It is not an easy astronomy textbook. Thank God that you weren't born in medieval Europe, because let me show you what your astronomy, actually nobody even reads the book anymore, so what am I worried about? But if you did read books, then you would know that The Almagest was not a fun astronomy book to read. I've tried to read it. I've got it on my shelf back here. It features diagrams like this with rotating circles on top of rotating circles and complex geometrical arguments. It's kind of beautiful. It's considered a classic of the ancient world today. Could I find a larger picture here?
So did he win his argument by confusing the hell out of people?
No, actually, some people argued that he did that, but the reality is the reason why he didn't confuse the hell out of people is, yeah, if you were a person like some ancient cleric or priest who had the time to study these kinds of things, a court astrologer, you would slowly be able to figure out his argument. But the way he made it more accessible to people is he published a table at the back of the book. So at the back of the book, he published what we would call an ephemeris. We still call them an ephemeris today. And the ephemeris is a table of the rising and settings of planets and eclipses. It's a table of planetary motions. We actually used one last week when we looked up the coordinates of the planet. So although the model was confusing, John, you didn't have to be a rocket scientist to look up the planet you were interested in and get its rising and setting times from the book. You see what I'm saying? The model was confusing, but the results were easy to understand. And this book was used for 1,500 years as sort of the Bible of astronomy. In fact, the only reason they even stopped using it 1,500 years later was because the model was not philosophically true. Over time, there developed larger and larger errors and discrepancies between when he said an eclipse would happen and when the eclipse actually happened. At first, it would be off by 30 minutes, then it would be off by a few hours, then it would be off by a day. And then people began to realize that this model couldn't be the end of the story. But if you were an ancient Greek or Arab living in 500 AD, you would have thought that humans had solved the problem of astronomy because you knew how everything worked and you could predict the positions of planets. So what was there to argue about? It was only after thousands of years watching the model deteriorate that people began to suspect that something was wrong. And that's when Nicholas Copernicus came on the scene and put the sun at the center of the solar system. To learn the end of that story, you'll have to tune in to Wednesday's class. Okay, as an example of understanding how tricky eclipse prediction can be, we are going to do an eclipse prediction lab today. I can't help but notice I've only got 4 interactive humans today, and that's bothering me a little bit because I wanted to have more participants in that to justify me doing these sessions. I'm still going to interface with you guys live because I know you're appreciating it. Otherwise, you wouldn't be here. But I would like to get more people involved in this class so that I know I'm not, you know, I want to know that it's worth doing this and not just giving you the videos like the other professors do. So that's something to think about, not for you guys, but for the trolls who are hiding in the background. Who are my trolls? Jamie, Kyle, Ashley, Michael, Ryan, Zachary, Naomi, Valentina, Yudi, and Molly. Trolls, okay? Maybe you guys should think about. Actually, Ryan I forgive because he doesn't have a camera and he participates a little bit. Okay, so I forgive a little bit. Anyways, let's take a little tea break. I'm gonna get a snack and then in 15 minutes or so, we'll come back. It says 1:31 on my computer. It says 1:35 on my cell phone. So 45 at 1:50, we'll reconnect and we'll start lab 3. Sound like a plan? Okay, I'll see you guys then.
Copy.
Okay, everyone. Welcome back. We're about to do lab number 3, eclipse prediction. While my phone charges, why don't we go ahead and review a couple of the rules for eclipses, because what we're going to do today is a little confusing. It's not very hard. You just kind of have to learn how to get started with me. The right way to do things is for you to start by looking into your notebooks and reminding me what are the 2 conditions for some type of an eclipse to occur. You should have that a few classes ago under eclipse conditions. So what are the 2 conditions we have for some type of an eclipse to occur?
The phase of the moon needs to be either new or full,
Good.
and the moon must be at with the wait a minute, hang
At
on.
an N,
Node.
at a node. And what does a node mean, Kim?
Is that where the moon crosses the path?
The path of the fill in the blank.
Ecliptic plane.
Ecliptic plane, beautifully said. So let's look at that in a little more detail, Kim. I'm going to try to get out a couple of globes here. Let's make this be my sun. And, geez, I guess maybe I'll use this little guy here. This little guy will be my Earth, okay? It would be nice if they could be at the same height. Let's see if I can use this software box to get my ecliptic plane in the right position here. Maybe just a little higher. Maybe just a little bit higher. We've got to look at those eclipse conditions. All right, okay, we can work with this in just a little bit more detail. Oh, fuck. Jesus, hold on. Hold on. Oh, okay. Sorry, my hard drives went over the edge there. Not good, not helpful. Okay. And let's get a move. Here's the moon. You guys remember that the moon does not orbit the Earth in the plane of the ecliptic. So let's think about where the ecliptic plane is.
I basically want to farm until I get a whole lot of these cottons. Now, back here,
John, let's mute yourself just for a second because that background radio chatter is distracting me. Is that you?
Oh, I'm sorry. I didn't realize it was me.
Oh, that's okay. All right. So if you need to contribute, John, just unmute for a moment. So here's the ecliptic plane. The ecliptic plane is the Earth-Sun line. Let's pretend this is the sun and this is the Earth, okay? It's not that the moon is orbiting in the plane of the ecliptic, but the moon's orbit is inclined 5 degrees with respect to the ecliptic. So sometimes it sort of comes up like this. By the way, a node is when the moon crosses the ecliptic. So when the moon is coming up, we call this an ascending node. That's when it's going up above the plane of the ecliptic. And when the moon is coming down, we call that a descending node. A descending node is when the moon is traveling down. Now, the conditions we made it sound like in class were a little bit too simplistic. We said that the phase of the moon has to be new or full. Let's test your knowledge just to make sure I'm working with some reasonably educated people here. Here's the moon in between Earth and the sun. What's the phase of the moon? Please make me happy.
New moon?
Is it, yeah, new moon?
Right. And so what type of an eclipse would this make?
Completely blacked out?
Solar versus lunar.
Solar eclipse.
A solar eclipse, right? Yes, it would black out the sun, Jenna, but not completely always. Okay. If you think about it, the date and time at which the moon goes into new moon phase is never going to be the exact same time as the node crossing. It just will never work out that perfectly. What's more likely to happen is the moon will be coming up on an ascending node. First, it will cross the ecliptic plane. You guys can't see this, but my moon is a little bit in front of the line here. But then the moon will actually, shortly after crossing the ecliptic plane, it will go into new moon phase. Now, the moon doesn't have to be perfectly on the ecliptic plane to block the sun. It can be a little bit north or a little bit south of the ecliptic plane. The problem is you'll get an eclipse if the time of the node, the time when the moon crosses the ecliptic plane, is close to within about 28 hours of the exact time of new moon. Now, the exact time of new moon is when the moon is on a kind of vertical alignment with Earth and the sun. The exact time of new moon is when the moon crosses this kind of vertical plane. So it's sort of in between Earth and the sun, but it could be a little bit up or a little bit down, as long as it's on this vertical plane is perpendicular to the ecliptic, but I don't know what its name is. It's been lost to time or to me, but it's perpendicular to the ecliptic. So this is the time of new moon when it's exactly in vertical alignment. The time of the node is when it's on the horizontal alignment, and they're never going to happen at exactly the right time. Today, we are going to play Where's Waldo for eclipses, and we're going to hunt down 2 solar eclipses and 2 lunar eclipses during the year 1999 so that you guys can see some of the tricky nuances of doing eclipse prediction. Okay, so let's try to get right into that. We'll have those around if we need more demonstration. Okay, let's grab the phone. Let's see if we can connect to Zoom, which is what I usually like to do. Share screen, iPhone, share. Pray to the technology gods. Yes. Zeus Poseidon is with me today. Come on, baby, connect. Yep. All right, there we go. Okay. So here's our page. Let's put you into the tape roll here. And as always, the first thing we'd like to do is put our name down on the page. Let's not forget that this is lab number 3. By the way, I need you guys to be careful. Some people are turning in homework number 2 as homework number 3. Some people are turning in lab number 2 as lab number 3. If you do that, I'm going to give you a 0 because you can't follow instructions. So I need you to be real careful about that stuff. That's why I always have you guys write down the number of your homework and the number of your lab on every page. Please pay attention to that when you submit, okay? Your section is AS1010 and whatever your section is, I don't know. It's either 001, 002, or 104. That will help me when I have to identify you, all right? Okay, we got 2 sheets to work with here. One is the data table where we're going to collect our eclipses. So here, the top column is for solar eclipses. The bottom column is for lunar eclipses. We are going to hunt down 1, 2 solar eclipses and 1, 2 lunar eclipses. And the first thing we'll be looking to do is write the dates and times of the eclipse. Hold on, guys. I'm going to just sharpen my pencil for a second. Sharp pencils, sharp minds. Okay, this table gives us the dates and times of new moon, full moon, the ascending node, the descending node, the perigee, and the apogee. Does anyone remember what these 2 words mean, perigee and apogee? Okay, let's take a cheat sheet note. This means close to Earth, and this means far from Earth. Okay. Over here, You guys already realized that the new moons are going to give us solar eclipses. Thanks to John for reminding us of that. I think it was John. The full moon are going to give us lunar eclipses. And every year there are 2 eclipse seasons, which mean you normally get 2 of each type of an eclipse. Now here we're going to have to talk about the conditions. First of all, let me just orient you to something. There is not only a date of new moon, there is a time of new moon. And this might be confusing to you guys. You might be wondering, wait a minute, I know that the new moon is on a certain date, but what's the exact time of new moon? Remember that if you have sun and earth, there's kind of this vertical plane that cuts through the middle of them. The date of the new moon is the date when the moon is swinging through, and when it gets right in between, it doesn't have to be in between them on the ecliptic plane's path. It could actually be like a little bit up here or a little bit down there. But the date of new moon is the date when it cuts through that vertical plane between Earth and the sun. On the other hand, the dates of the nodes, I'm going to attempt to do this in 3D and probably fail. Let's make the ecliptic plane a horizontal plane, and I'll kind of shade it in as if I had good art skills. The date of the node is when the moon is slicing through the node, the ecliptic plane here, which might happen a little bit before or after it goes through the vertical plane. I hope that made some kind of sense to you. Now, there are conditions for an eclipse. Of course, the time the moon goes through the vertical plane is never going to be the same exact time that the moon goes to the horizontal plane. So here's our first real condition for an eclipse. If the time of the moon is less than 28 hours from the time of the node, then pow, you will get an eclipse. 28 hours is the key time differential. Obviously, if the moon and the node happen at the exact same time, you're going to get one hell of a whiz-bang eclipse. But they can be off by as much as 28 hours in either direction, and you'll still get an eclipse. So have you guys ever played 21 blackjack before? We're going to be playing 28 blackjack today. We're going to look at the time of the moon and the time of the eclipse. If they're less than 28 hours, we have an eclipse. If not, we're busted, okay? So you see, we're going to compare the new moon, where we have solar eclipses. We have to compare them to both the ascending node and descending node to see if this time of the moon could be within 28 hours of either one of these. Now let's think about 28 hours for a second. 28 hours means we need to count hours anytime we are 2 days apart or less. And here's why. Let's imagine we had a Monday, a Tuesday, and a Wednesday. I could have a new moon, which occurred at 2300 hours. So that could be my new moon. And I could have a node on Wednesday, which occurred at 100 hours or 1 o'clock. In that case, they would be separated by Tuesday, which is 24 hours, plus 1 hour into Wednesday is 25, and 1 hour in Monday is 26. So this would actually constitute an eclipse, even though the dates were actually 2 days apart. So anytime dates are 2 days apart, like they are here, we're going to have to count the hours. First thing to do is just to remind us that we're going to be using a 24-hour clock. I've found when I'm doing this with students in the lab that, someone like John might be used to working in a 24-hour clock. The rest of us, not so much. So even just writing down the numbers 0 through 24 will help if we get confused and need to count hours. I've found that this turns out to be a useful exercise. Every time I do this lab, we'll be the judge of that soon enough. And that's just so that if we have to count hours, we can kind of count them visually in a 24-hour clock. Okay. let's go through, and I'm going to walk you through the finding of one of our solar eclipses because it's kind of very confusing to get started here. So why don't we look here? Let's make our job a little bit easier for counting hours. This is January 17th at 1546. I'm going to round up, and I'm just going to round this off to 1600 hours. That's just to make the counting of hours a little bit easier. Class, can there be a solar eclipse between January 17th? So we're going to ignore the lunar for a second. We're going to compare solar to both ascending and to the descending nodes. Can I have an eclipse between January 17 and January 5? Yes or no? No, says Noah. Why not?
Because they don't occur within that 28-hour window.
Yeah, they're more. Another way to say it, no, is they're more than 2 days apart. Okay. How about, because whether or not they can be 2 days apart and not occur within the 28-hour window. That's the problem we're facing. For instance, Noah, let's look at January 19 and January 17. Those are 2 days apart, but it's not obvious to me yet whether it will be an eclipse or not. So now we have to slow down and count the hours. Okay. To do that, let's start by rounding off this to 14 o'clock. Now the node can be before or after the moon. Which came first today? It looks like the moon was first and the node was second, so we're going to count some hours. John, let's get your help because you're probably good at this. How many hours would be left in January 17th if we're starting at 16 o'clock? Sorry, you're muted, bud.
So that'd be 3 o'clock. So you have 9 hours left before midnight.
Wait, let's not convert it back into 12-hour time.
Okay.
Let's stay in 24-hour time so there's no ambiguity. If you do get confused, you can use a calculator and subtract. For instance, you could go 24.
So it'd be 4. So it'd be
8 hours, right?
yes, sir.
Because 4 hours gets you to 20, another 4 gets you to 24. Okay, so we have 8 hours in this day, but remember something comes between Jan 19th and Jan 17th. That's of course Jan 18th. How many hours will be in that day?
24.
So now we have to take the 8 and add them into 24. We're busted. So there will not be an eclipse on Jan 17th. Let's move on. Let's try Feb 16th. Once again, we're going to round this to 700 hours so we don't have to count. Counting minutes is a real drag and it's probably not helpful. Okay, jumping Jesus. It looks like there were 2 ascending nodes in the month of February. How could that be possible? Wait a minute. What is the sidereal period of the moon anyways? The sidereal period of the moon is 27.3 days. So it's possible to have 2 nodes in the same month because months are usually 30 days, you know? Okay, we're gonna have to compare it to this node, and this node. Sorry, life just sucks sometimes. Okay, Feb 16, Feb 1st. Can there be an eclipse there? Yes or no?
No.
Feb 16, Feb 28. Yes or no?
No.
Feb 15 and Feb 16 is 1 day apart, so we better count the hours. Let's round this to 22 o'clock. Where do we start counting? We start counting under which day comes first. In this case, Feb 15 comes first. How many hours are left in that day?
2.
Now we add that to the number of hours into Feb 16th. 2 plus 7?
9.
I think we just found ourselves an eclipse. Booyah. Okay, we found our first solar eclipse, but what do you think is the mid time of the eclipse? Would it be the time of the moon or the time of the node? Take a wild guess. Just
The
guess.
moon?
I'm in the new moon.
That's right. The reason why has to do with this fact. If this is sun and this is earth, if this is the vertical plane, and then if I try to shade in the horizontal plane like I did before, this is probably not going to work, but I'm going to try it. The moon, as it swings through, can hit the ecliptic plane before, it can hit the ecliptic plane after, but the time of mid-eclipse will be when it's on the kind of the vertical alignment between Earth and moon. That's when it's going to block the greatest amount of the sun. So what we will use for our time, this is, by the way, these are universal times, Feb 16th at 6:39. So let's just write that in. Okay. In our next statement, we are going to convert it to local Eastern Standard Time. They ask for AM and PM, but screw that noise. We want to keep this in military time so we don't screw it up. All right. Now, here's our second rule for eclipses. To go to Eastern Standard Time, which is what we are on right now, Eastern Standard Time is universal time minus 5 hours. But remember, we have daylight savings time. Eastern Standard Time only lasts from October through April. So basically, Eastern Standard Time is winter months. In the summer, we have Eastern Daylight Time, daylight savings time. And when we do that, we do universal time minus 4 hours. That goes from approximately April to October, or summer months. You'll notice that this was a winter time eclipse, so we have to use Eastern Standard Time. We will subtract 5 hours. February 16th, if you subtract 5 from 6, you get 1:39. That's the local time in Rhode Island that this eclipse will take place at, or did take place at, because this was the year 1999. Okay. The next question we want to ask is central or partial. Central eclipses, central solar eclipses, could either be a total solar eclipse, or it could be an annular eclipse, because both total and annular eclipses are centralized. So that's central. Partial eclipses are when the moon only blocks a portion of the sun. So they're not centrally located. The rule of thumb goes like this. You get a central eclipse, or in the case of a lunar eclipse, we call it an umbral eclipse, if the time of the moon and the node are less than 20 hours. But you get a partial solar eclipse, or in the case of the moon, we call it a penumbral eclipse, if the eclipse was between 20 and 28 hours. So how close the moon and the node are determine whether it's central or partial. Do you guys remember how many hours separated Feb 16 and Feb 15? Who's got a good memory? I guess I could make you count it again, couldn't I?
Was it 9 hours?
That's right. So which condition do we have here?
Central umbra?
Central. We'll save umbral for the lunar eclipses. The next question is tricky. They want to know if the thing was north or south of the ecliptic plane. To do that, we're going to have to take a look at whether we were at an ascending or a descending node, and also the times. So let's do this for question 4. Let's make ourselves a dashed line somewhere on the page, and let's label it E for the ecliptic. That's the representation of the ecliptic plane. Stay with me here because I'm going to move kind of quick. Okay. Did our eclipse happen during an ascending or a descending node?
Descending.
Okay. So that means the trajectory of the moon was heading down through the plane of the ecliptic, with this being the node. The node occurred on February 15th. Did the eclipse happen before or after the node?
Before?
After?
Why after, Jenna?
Just because it says February 16th.
That's right. We have to look at the date first. Feb 16th is after. So Jenna and Kim, the moon was heading down through the ecliptic plane. You had the node first, and then the moon alignment happened on the 16th. Was this eclipse north or south of the ecliptic plane?
South.
South. And that's how we have to figure this out every time. We have to draw that little diagram. Okay, total or annular has to do with whether our central eclipse completely blocked or partially blocked the sun. And that has to do, you'll remember from our homework, with where the moon is in its orbit. If the moon is close to the Earth at perigee, the angular size of the moon will be very big and it will block the sun. If the moon is far from Earth at apogee, you'll remember that its angular size will shrink down to like 0.48 degrees, and then it won't block the sun and you'll get an annular eclipse. Here's the rule of thumb for this. If the moon is less than 8 days of apogee, then you get an annular eclipse. If the moon is more than 8 days of apogee, you get a total lunar eclipse. I don't know why I said annulars, sorry. Okay, our eclipse happened on Feb 16. Our apogee was Feb 9. How many days apart are they?
7.
7. That means we actually got an annular eclipse on this day. The last question is pretty easy. Was this solar eclipse visible from your location in Rhode Island? What time did the solar eclipse happen in this case?
Military time at night.
Military time at night. So do you see where I'm going with this, John? If a solar eclipse is happening at 1 a.m., are you going to see that solar eclipse?
If I was on the other side of the world.
Right, maybe, but it doesn't guarantee because the eclipse is still a small shadow, but you're certainly not going to see it if it's at nighttime. That's why they said possibly, not definitely, okay? No, because you're not going to see no sun at 1 a.m. Okay, now here's my test to you guys. I just showed you how to do this. Can any of you, let's play Where's Waldo together. We're doing it live. Can anyone find me the second solar eclipse before I have to tell you where it is? Remember, the sooner you're finished, the sooner we can all go and eat oatmeal. So can you find me another eclipse that's less than 28 hours from the node? Why don't you take a moment to hunt for that? I'll have my camera held up here just in case you don't have the sheet handy for you. See if you can find the next solar eclipse. Go ahead systematically and compare the time of new moon to the ascending and descending node. Whoever gets it first wins at astronomy for today. So let's see who can find it. I'm trying to hold my hand steady. It's not that easy.
July?
Okay, let's look at July for a second. Oh, shit, okay. Get the fuck out of here. Okay. You're saying July 13th, Kim, with what date? If I draw on this, can you guys see my drawing here? Did you see that? Can you see the red drawing? Yes, okay. So Kim, you're saying this
Yeah.
date, July 13th, right?
Yep.
And
then it's
what's
July 14th.
Okay, let's count. Let's call this 2 o'clock. Let's call that 16 o'clock. Which came first, the moon or the node?
The moon.
How many hours are left in that day?
22.
22 hours in this day. But now you have to add the 22 to 16 for the next day. 22 plus 16,
Okay.
you're busted, aren't you?
Yep.
So that actually doesn't work. But I'm glad you suggested it because it was useful to do it.
This is August 11th.
Yeah, look at this.
But Jenna was going to say it first. I just jumped over.
Oh, that's
No,
okay.
No, you're good.
A couple of you probably were looking at the next one thinking, holy crap, those are on the same day. That almost has to be an eclipse, right? How many hours apart are these? Can you do it without me? Call that 2, call that 11.
Is it 13?
No,
9.
9, right? It's 2 p.m. versus, sorry, it's 200 hours versus 1100 hours, right, Jenna?
Oh, okay.
Don't use AM and PM, they screw you up.
Mhm.
This 11 minus 2 gives you 9. You do believe that, right, Jenna?
Yeah, I think I accidentally added the 2 instead of subtracted.
Okay, that can happen. All right, so we know that our next solar eclipse is August 11th at 11:08. Let's get back to the game here. We'll write August 11th. (11:08). Okay, our next question is to convert that to Eastern time. Are we Eastern Standard Time or are we Eastern Daylight Time?
Daylight.
Right, so we got to do minus 4 hours. So that's still August 11th. 11 minus 4 is 7. That's 7:08. Central or partial? Was this less than 20 hours or more than 20 hours apart? What did we decide?
Less than?
Yeah, it was like 9 hours. So this is still central. Now let's see if you guys can do the north or south thing. Once again, we'll make our ecliptic plane, dash, 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 dash. Was this an ascending node or a descending node, August 11th?
Ascending.
So now we're going up. This is the date of the node, or rather we'll use the time since they were the same date. The time of the node was 2, right? What was the time of the eclipse?
$11.
So 11 comes after 2, so if it's heading up, 11 will be up here. And what's our answer?
North?
People like Ptolemy and the guy who discovered Saros cycles, the 11-year cycles of eclipses, they were able to do all of this thousands of years ago. Okay, total or annular has to do with whether or not you're 8 days from apogee. Apogee in August was on the 20th. How many days apart from the 11th is that?
It's 9 days.
So which one are we then?
Total eclipse?
Yeah, that would have been a total solar eclipse. Lastly, would it be in theory possible to see the solar eclipse at 7 a.m. in August? Yeah, I'd say you might be able to see the sun at 7 a.m. in August. Whether or not you would see the total or the partial eclipse would depend upon where you were on Earth. That's why they say possibly visible. Okay, now let's hunt for the new moons. Let's hunt for the lunar eclipses, which happen on full moons. Do you guys want to see if you can find, let's go back to that table again. See if you can find, at least one of the lunar eclipses. One of them's hard. Hey, I want to point something out. Do you guys see this here? Do you see how there were 2 full moons in the month of January? That's pretty weird, right? How many days are in January? What's that,
31.
Jenna? 31. But do you guys remember what the synodic period of the moon was? How long does it take the moon to go through a set of phases? What's the synodic period of the moon?
Was it 25 days?
No, it's longer than the sidereal. It's 29.5 days. Meaning, if you have an eclipse, I'm sorry, not an eclipse. If you have a full moon right at the beginning of a month, it's possible to have a second full moon in the same month. Do you guys know what they call that? The second full moon in a month? They call it a blue moon. Blue moons are supposedly rare, but how many blue moons do you see happening in the month or in the year 1999?
2.
Yeah, there's also a blue moon down here. So they're not as rare as you might think. Okay, see if you can find me just one of those lunar eclipses. It's the same rule, less than 28 hours. Meanwhile, I'll take a nap while you guys do all the hard work. You should be comparing your full moons to both the ascending and descending nodes, trying to figure out if one is less than 28 hours.
Is July one of them?
Okay,
The
so let's
28th.
check this out.
Nine.
And which node are you comparing that with?
The descending node?
There are 2 descending nodes.
Oh, July 29th.
Okay, let's count some hours together, Jenna. Let's see. This comes first. How many hours are left in that day?
13.
12 or 13. How many hours into this day are we?
2 or 3.
Yeah, so 16 hours is less than 28. Bam, you found one. Nicely done, Jenna. So let's write down the time of the moon, July 28th at 11:25. Good job. Okay. Let's do all our work before we hunt for the next one. Is this Eastern Standard Time or Eastern Daylight Time that we're converting to here?
Daylight.
Okay. So we got to subtract 4 hours. July 28th, 11 minus 4 gives you 7 again. Was this umbral or penumbral? And it's the same rule as before. Was it less or more than 20 hours apart? What did we count up there, Jenna? Or friends?
13, was it?
Or more, like I think it was actually like 16. So it's definitely penumbral. Would we be able to see a lunar eclipse at 7:25 o'clock? John says no. Why not?
Because it's July, it's the summertime. The sun's already coming up.
Probably, yeah. But you can see the moon during the day sometimes. Here's the bigger question, John. when does the full moon rise and set? Do you remember that? I actually took this as some notes at one point. I want you guys to know the rising and setting times of the full moon. I believe that's important. So let's review it since you've forgotten.
Oh.
Yeah, Jenna.
It rises at 6 p.m. and sets at 6 a.m.
Right. So chances of seeing this lunar eclipse, because remember, John, the only thing I'd say about the daylight is it's not the same as solar eclipses. You can see the moon during the day. Do you agree with me? Then in theory, you could see a lunar eclipse during the day. But in this case, the full moon is up all night. Well, in a way, John, you are right. During the day, you can't see the full moon, so you can't see lunar eclipse. Sorry, I actually just proved you right and me wrong, okay? So John, you were right for the original reasons. It's during the day, sorry. Okay, so no, you can't see this lunar eclipse. Sorry about that. Okay.
I was about to say, if it passed through the sun during the day, it would be a solar eclipse.
Well, no, because the Earth is in between the moon and the sun during a lunar eclipse, right? In any case, you were still right. So just quit while you're ahead and don't say nothing, okay? The last lunar eclipse is really, really hard to find. I'll tell you where, I'll tell you where it is. Ryan, I don't know what Ryan was. Oh, Ryan was answering a different question. Can you guys find the other lunar eclipse? It's really hard. You might want to look for an eclipse that happens, you know, maybe around a blue moon. While you're hunting, I'm going to look something up here. Anyone find it? Usually one person can find it, but it is tough. I gave you a hint.
Is it the March 31st to ascending node March 28th?
Let's see, March 28th happens at 1 o'clock, right? There's 23 hours left in that date. And then in March 29th, there's another 24 hours. So you're already almost at 40 hours, right? Or more.
Yeah.
I didn't do the math, but January 31st and February 1st.
There you go. Look at that. Because look, January 31st, how many hours are left in that day if it's 16 o'clock? 8, right? Sorry, because 16 to 4 is 20. 20 to 24 is another 4. But what is 8 plus 13 equal to?
21.
21. And you are not busted because this is 28 blackjack, right? So bam, we found our next one, which is January 31st at 16:06. A blue moon eclipse. Oh, sorry. You guys are still seeing you're not seeing my live phone again, are you? Is it frozen for you guys?
Yeah, it's on the sheet.
Well, I
It's frozen.
reactivated. Oh, Jesus, hell. If I stop sharing, I'll never get it back. That's what I'm worried about. Try. Gotcha. I got you. I hit it quick. Give it a second. All right, it's thinking, come on, baby. Oh, it says check mark. Unable to connect. Hold on, guys. All right. It's sucking. It's not working. Okay, for the final bit, how am I going to do this? Okay. Let's try a different method. We're almost done, so I'm just going to do this crudely. Ready? Here we go. Not as great, but we can work with it. Let me adjust the focus. See if that helps. Okay, there we go. All right, so what's our local date and time? Is this Eastern Standard Time or Eastern Daylight Time?
Standard.
So we have to subtract 5 hours. That's January 31st, I guess 11:06, right? 11 plus 5 is 16. Good. Umbral or penumbral? How many hours apart were these guys?
Is it umbral?
Well, this was 8 hours plus 13 gives us 21.
Oh, so it's penumbral?
Yeah. I guess, yeah. I thought one of these was umbral. Did we do this one bad? July 28. 12. Oh, wow. Yeah, we did this other one bad. Look, July 28 happens at like 12 o'clock. 12 plus 2 is 13:14. It's clearly, do you see that we made a mistake on this one? Sorry about that. That was some sloppy work on my end. This one's penumbral. Can we see the moon at 11 o'clock, John? No. Okay. And these are our answers. We have done a little bit of eclipse prediction together. Now, you guys get all that data? All right, there's one last thing I'd like to do with you guys. We have some NASA footage of that first eclipse from 1999, the blue moon eclipse. Would you guys like to see it real quick? All right, here we go. There you have it, guys. Direct from NASA, right to your eyeballs. Okay.
Thank you.
I think we all needed a good laugh.
Yes, I know. I know. This one's a bit of a head scratcher. Now, let's think about what we learned. We learned that you can predict eclipses, but that it's kind of freaking hard. And the key idea is that the time of the moon and the time of the node, unlike we talked about in class, never perfectly line up. And it's all about timing differences, what type of an eclipse you get. So I don't know. I've learned to like that lab. Maybe you will with time. Does everyone have it down, know what to do? You're going to submit this right away and not forget, right?
Sunday, right?
Well, I graded on Sunday, so it's got to be submitted before then, okay? Yesterday, I graded I put it off until 10 p.m. So I've been grading at 10 p.m. That's, I don't know, one day I might start earlier, but someday, at some point Sunday evening, I grade. And when I grade, that's when I deactivate the submissions. So, but you guys clearly stuck it out and did it with me live, so you might as well submit it now before you forget, okay? On Wednesday's class, we will learn about heliocentrism, and we will do a homework on the history of astronomy involving some of this stuff. So I look forward to seeing you guys then. Any other questions for me?
Thank you.
Thank you very much. Take care.